Hi. Hi, everybody. I guess I shouldn't have to introduce myself as David Wallace, since participants and people from the Stats Lab might be expected to know me. Just 10 seconds. This is a really symbolic event and occasion, because as you all know, we used to keep the back door locked to all the academics in CMS, and now you can come and get your cards accredited, so you can even come in the back door. To think that we have the confidence and courage of the community out there actually to hold a special meeting with the Stats Lab this afternoon. I should say as well that I said to Mike, I want to just make a brief comment that this is symbolic. He looked at me and said, shambolic? No, it's symbolic. Mike, over to you.
Thanks, David. Welcome to everybody home and abroad. Hope we didn't have any trouble with the traffic. Maybe you didn't. People thought it did. Anyway, we're very pleased to have this event this afternoon, and I'd like to thank Phil and his colleagues for arranging the programme. And I think without more ado, invite Bobby to give the first presentation.
Thank you. Okay, so this is a little bit of work that I did with Juhi Lee of Fidelity Investments. Juhi and I met last year because she's a former Cambridge PhD student, and she wanted to propose an MPhil project. We have an MPhil in statistics, and she proposed a project, and I got to assign to be the internal advisor, and it very nicely turned into a collaboration. So this is a little bit of things that I've been doing with her on estimating covariances. Oops. Okay, so we're dealing with financial assets. There'll be a little bit of finance in this talk. This talk is aimed at the finance community, but I always apologize for not really being knowledgeable about finance, but you'll probably find it a little bit low on the statistics side. So assets begin being publicly traded at different times. So we can have a time series of returns for a stock, say, or hundreds of stocks, and because companies begin conducting business at different times historically, their publicly traded assets begin having returns at different times. It's also true that they can close for various reasons, and you can talk about how companies which have merged or gone bankrupt can affect the prices of other companies, but I won't be making much about that here. I'll just be focusing on historical missingness in asset prices and returns, and how this can make estimating covariances between assets challenging. And why might you want to do this? Well, because you want to do mean variance portfolio rebalancing or something like that. So estimating covariances is challenging when there's missing data, when you have uneven lengths of histories for different assets, but there are algorithms, and most of them go as treating it as a missing data problem. So what are we talking about here? So the columns in this picture represent time series of returns, and the most observed asset is in the first column, this one right here, Y1. It has N1 assets, and N1, or N, is the total number of returns that we have for the entire time horizon that we're considering. And every other asset, as we're going to the right in the columns, has fewer than N, or fewer than N1 returns. And I've ordered the asset in this way, and if you can do that, if you can order the assets in this way, and all of the missing data, which in this case is historical, can be pushed to the bottom right, then the missing data pattern is called monotone. Or in other words, if we do not have an asset observed at this time here, then we don't have one observed for that time for any of the assets to the right. And there are, of course, lots of ways that you can say the same thing. Here, time is running to the reverse, so time 1 a long time ago is down here at the bottom, and time n is now. The index we'll be working with is the reverse of that, where time 1 is, or index 1 is today, and the oldest time is index n. Okay, so just a bit of notation. The collection of all of these time series, which we're eventually going to be treating as independent for estimating covariance purposes, is just collected in this matrix Y, where some of the entries are not available, and the columns are just indexed by bold lowercase y, and J is the jth column. Remember, I don't have to walk over there to change the slide. Okay, so just formally, a missing data pattern is monotone if the ijth entry is not available, if the return of the jth asset is missing, and monotone is ij is available whenever ij plus 1 is available. So yij is not NA whenever yij plus 1 is not NA. We're going to be assuming missing completely at random. That's an assumption that's pretty strong and is not entirely necessary, and we'll not go into other assumptions like this because we won't be that technical in this talk. But it turns out that when you have a monotone missingness pattern, the likelihood that you get, no matter what distributional assumptions you make, has a convenient factorization that makes for nice maximization if you're interested in maximizing the likelihood. So that is, you can maximize each of these conditional components separately and maximize the likelihood of the parameters of interest based on the set of data that may be partially missing. We're going to be dealing with multivariate normally distributed data. And in this case, maximum likelihood estimators are particularly easy to construct. So the interesting parameters for maximum likelihood, for multivariate normal distribution is, of course, the mean vector and the covariance matrix. And we're going to be proceeding iteratively. We're interested in estimating, say, for the jth asset, its mean, and then sigma 1 colon j, which is the jth column of the covariance matrix. And it turns out that each column of that covariance matrix and each mean component of the mean vector can be found by a simple regression. So we'll talk more about those regressions, but basically the idea is that you regress the jth response on the previous j minus 1 responses where there is data available. So this bold y subscript j is all of the data available that's completely observed for the first j minus 1 assets where the jth asset is observed. So it's a little bit hard to say that in words, but the picture is that if we want to learn about the jth component of the mean vector of these assets and the jth column of the covariance matrix, then all we need to do is regress the fully observed portion of the jth column, or here the fifth column, on the same proportion of observed data in the previous 4 columns. And when we do that regression, there's a nice formula that turns those estimates of regression coefficients beta j into estimates of the mean and the covariance matrix. Okay, so when you can do these regressions, and of course that's going to be the point of the talk, so when the rank of this design matrix for this jth regression is, when it's a full rank matrix, ordinary least squares gives the standard maximum likelihood estimators of the regression coefficients and of the noise. So these regressions give rise to what I call the mono-MVN algorithm, which is just concatenating monotone and multivariate normal together, which is start out by doing the straightforward estimator of, or maximum likelihood estimator of the mean and the variance of the first column, the completely observed column, and that's just an average and a difference of squares. Then you can proceed iteratively from, I should have put j equals 2 to m, but of course this works for j equals 1 as well. We can obtain the next estimate of the mean and covariance column of the covariance matrix from the previous means and columns of the covariance matrix by doing a maximum likelihood estimate of the regression coefficients and of the variance, and combine them into the next component of the mean vector and next column of the covariance matrix by these formulas. This isn't work that I've done. This is quite old. If you pick up a book, any book on missing data that's published sort of before the 80s, then it'll probably have this algorithm in it for multivariate normal data. I got this particular version from Little and Rubin's book. So what I'm going to be talking about is when this method fails. And of course, it fails when you can't do those regressions. So if it turns out that the design matrix in each of these iterated regressions for different columns j is rank deficient, then you can't invert x transpose x, or in this case, yj transpose yj. And this is what this conference is all about. This is a big P, small n problem, unless it happens that you have small p and just collinear input vectors, which could also happen. But basically, the point is you can't do these regressions when you have more parameters than you have observations. In the context of the financial inference problem, that means you can't apply this algorithm if you have an asset with fewer returns than the number of assets, which have, so basically if we go back to this figure, if we can't do this regression, if we have any asset where there are fewer returns than the number of assets which have more returns than it, then you can't do this algorithm. And in particular, you can't do the algorithm if you have more assets than returns. So if you have 2,500 assets going back 10 years with weekly data, then you can't estimate the correlations between all of those assets. So what do? We do what you might expect. We replace ordinary least squares with something that doesn't involve directly inverting that rank deficient matrix X transpose X. So instead of doing ordinary least squares regressions, we do shrinkage or change of basis. I don't need to go into the details. I have a quick slide on each one that I'll probably just skip over. But we're going to be doing a comparison amongst a variety of them: ridge regression, the lasso, principal components regression, and the partial least squares. And just to focus on the regression problem for a moment, I'm just going to be referring to capital bold X as capital bold YJ, and Y without a subscript as the jth column of the regressions that we're doing in this monotone missing data setup. So we all know how ridge regression and lasso sort of fit under the same family, and that ridge regression is a bit easier to do for a fixed choice of the penalty parameter lambda. It's basically the same formula as with ordinary least squares regression, except for this matrix is going to be invertible as long as lambda is positive. And for the lasso, more effort is required. You either need the Lars algorithm or quadratic programming. But an advantage is that with the lasso, you may get a lot of the components being shrunk to zero, which can be advantageous in a way that I'll talk about a little bit later. So, skip ahead? No. Okay, so change of basis algorithms are both based on SBD on particular matrices. So PCR, principal components, is SBD on the inputs only, and PLSR, partial least squares regression, is based on this SBD of something combining both the responses and the inputs. And so this is said to be the advantage of partial least squares regression, although in practice I think studies have shown that these methods are basically comparable. And also that principal components regression is related to ridge regression in an interesting way as well, that I won't get into anymore. So the important thing is how to choose these parameters, either the number of components in a principal components regression or the penalty parameter, and there are lots of ways to talk about to do this. The way that I'm doing it in this work is just by cross-validation, which I assume that I don't need to explain. So what's the algorithm? Just to summarize everything, there's really not that much to it. The mono-MVN algorithm is being augmented to include possibly one of these fancy regression models when they're needed. So we initialize the mean vector for the mean scalar for the first response by maximum likelihood, and its variance by maximum likelihood, which is the sample mean and variance of the first column of this big matrix. Then for the rest of the columns, we do regression to get estimates of beta and sigma squared, and if ever we need to, we'll use one of these fancy methods instead of ordinary least squares. And that'll give us the estimate of the next component of the mean vector and the next column of the covariance matrix. Okay, so I've phrased it as do these fancy regression algorithms only when you need to, but of course you can use them in other situations and possibly get benefit. So it's well known that these lasso and ridge regression estimators can improve accuracy and yield lower variance estimators. This is, of course, known as the bias variance trade-off. It can aid in interpretation, and by that I'm especially thinking of the lasso enabling the detection of zeros in the covariance matrix, because if there are zeros in the regression coefficients, those will filter through to our estimates of covariance and correlation between the different assets. So it might be fruitful to think about doing these regressions in situations when they aren't strictly needed. And so I've just thought about determining a threshold, kind of a straightforward thing to do, where you would do a parsimonious regression even if you didn't need to, depending on what the ratio is between the number of rows and columns in your design matrix. So this is something that I'm just going to be coming up with a rule of thumb for later. But the idea is that p equals 0 means always use the parsimonious method, no matter what. And p equals 1 is only when necessary. And everything else in between is somehow a trade-off between doing ordinary least squares and the lasso, say. Okay, so usually I've skipped over a bunch of places already in the talk where I normally do demonstrations, and that's what the finance people really like, but I usually have more time as well. But everything that I'm talking about is available in an R package. From the standard implementation of this inference algorithm, when you can do all the matrix inversions, to the fancy ones where you can't. And of course, I didn't re-implement all of this stuff. One of the great things about R is that folks out there feel the need to make their software available, and that's great. So that means that I don't have to come up with my own implementation of the lasso or ridge regression or principal component analysis. So my package that I've made depends on these packages. So that means that in addition to the lasso, I can also use forward stage-wise or stepwise or whatever other methods fall under the Lars framework. And you can try this stuff at home. All of the examples I'm doing today are in the examples part of the documentation of the package. So I want to do some comparisons just to kind of fill out the last 10 minutes. And I'm going to do this based on real data that I'll introduce in a minute and also some synthetic data. And in these comparisons, I'm going to compare all of the different types of versions of this algorithm depending on the regression method used to one another and also to some naive and state-of-the-art other ways of doing this. So two naive or simple estimators of the mean vector and covariance matrix are what I'm calling complete, which is to use only the completely observed cases. So that is only the rectangular part of the input matrix where everything is observed. There are no NAs. And then observed is to use all of the data, but in a naive way. So we'll just take each of the means to be the sample averages where the data is available, and each of the entries of the covariance matrix to be the entries that can be calculated with the data available. And of course, the disadvantage of this approach and of the complete approach is that the covariance matrices that you get won't be positive definite. But it can be proved that the ones that you get by this mono MVN algorithm are positive definite. And then I'll also compare to an algorithm that is based on EM. This EM algorithm was developed for arbitrary missingness patterns, so it's a bit more general. It works in situations where this monotone one does not, but its disadvantage is that it depends on initial conditions. It can get stuck, and when the missingness level is high, it won't converge, regardless of whether there's enough data to estimate the parameters or not. Okay, so first on some synthetic data, all I did was generate multivariate normal data where I sampled the mean vector from a multivariate normal distribution and the covariance matrix from an inverse Wishart. And then I randomly made it missing in a monotone way. So I introduced some uniform monotone missingness. And then I did inference under each of these different types of the algorithms and then compared the estimated distributions with one another. So I say distributions because I use Kullback-Leibler divergence to combine the mean and the variance in a way where it's actually the distance between distributions that's being measured. And then I also just did straightforward root mean squared error to the mean vector and the covariance matrix. And the take-home method is that what I was surprised by is that ridge regression is by far the winner on all metrics. It gives smaller Kullback-Leibler divergences to the truth with smaller variance and also smaller root mean squared errors to the actual individual components of the mean and the covariance matrix. And of course, second is partial least squares regression, and a close third is principal components. And the lasso, which has the nice property of sticking zeros in the covariance matrix, which is nice for interpretation, actually is a mismatch to the data generating mechanism in this case. I don't have the details on how big this experiment was, but it was just on 100-dimensional inputs with 1,000 observations from each. And then the monotone missingness pattern can delete up to, I think, all but 6 of the remaining observations in any column. So you're not in a situation where there are more more assets than observations, but you can be in the situation where you can't do some of those regressions by ordinary least squares. So I've set the p parameter to 1 so that parsimonious regression is only used when necessary. You can look at this same data and say, well, should we use ordinary least squares if we can, or does it make sense to always do one of the fancy ridge regression methods? And the answer is, of course, there's no cut and dry answer, but that an intermediate setting of how often to do a fancy regression versus an ordinary least squares regression is a good rule of thumb. So what's being done here is that I found the optimal setting of p under all these methods, and you can see that 95% of the time the optimal proportion was 0.6. 5% of the time it's very, very close to 0. If you compare ridge regression's performance to setting p equals 0, then p equals 0 will be better than p equals 1 90% of the time. But p equals 0.5 will be better than p equals 1 96% of the time. So I'm just arguing that it makes sense to some extent to use ridge regression even when you don't need it. But it doesn't necessarily make sense to use ridge regression all the time. And you may prefer a larger setting of p for speed reasons, because whenever you're doing ridge regression, you're doing cross-validation to find settings of this lambda parameter, and that can be quite a bit of work. Okay, comparing to this EM algorithm, which I've already mentioned the drawbacks of, and you can see that visually in the table. When you have 100 observations with 100-dimensional data, you find that EM, even with a uniform missingness pattern, is just not able to cope. It has good properties in its mean, well, not good compared to 3.9, but at least not astronomical. But you can see that these means and variances of, oh, I'm pointing to the wrong thing, I'm sorry. So the estimated mean vector was off by a huge amount, and it had a really large variance. And you can see the reason for that is because it had lots of cases which didn't converge, because 95% of them were quite reasonable, quite close to the true variance value, but many were not converged. But when you add more data in and give it more information, then it's more comparable. But you can still see that the mono MVN algorithm is a bit better, gives smaller estimates of the mean and with smaller variance. Okay, so just some real data to finish up. What we've done is taken data from the web, basically, which is 1,792 weekly returns over about a 30-year period, and then we did so with about 2,500 assets. So we're in the situation where we have more columns in the matrix than we have rows. The longest column is fully observed for 558 of these assets. So 558 of them have the longest return length. The shortest one has just 76 returns, and the overall level of missingness is nearly 50% of the observations are missing. A first experiment we did just to do another comparison between the different methods to see if, again, in this real data context, lasso and ridge regression are basically comparable. We used a complete subset and then randomly interjected missingness patterns and estimated mu and sigma and measured the distance to the fully observed counterparts. And the results, the ridge regression line is meant to be in bold again, but it's a bit hard to see. But the results of that ridge regression is, again, the best estimator. It has the smallest Kullback-Leibler divergence on average and with the smallest variance. It does not have the smallest of everything else. It has the smallest root mean squared error to the mean, but it's also very close to others nearby with a slightly larger variance. But you can see that where it's really doing well is in the estimate of the covariance matrix, giving very small variance estimates of sigma. And it doesn't make any sense to talk about ECM on this data because it just has too many columns to rows. So there's no EM algorithm for this that works. Okay, finally what we did was we wanted to learn something about the data that we downloaded from the web, and there's really no choice when it comes to what algorithm to apply. The EM algorithm doesn't work. The complete estimator uses only 3% of the data, and of course doesn't even give you positive definite estimates of sigma. What we did was, to learn something, we applied the lasso, even though that wasn't the best in terms of Kullback-Leibler divergence, but we wanted to see which of our assets were correlated with other ones, and which weren't correlated with any, and which were pairwise independent. So, and you can actually do that with the other Lars methods as well, but we saw that the lasso was the best of the family of Lars methods. Okay, so when we do that, we find that 36% of the maximum likelihood estimator of the covariance matrix is 0, which means that a lot of our assets are independent of one another, and 6% of the inverse of that matrix is 0, which means a lot of them are independent of one another, even conditional on, marginal of everything else. I think I have that backwards, don't I? Yeah, the more interesting thing is the next bit. So what, of course, there are market forces involved here, so a lot of these assets are going to be correlated with one another just because they're moving up and down with trends in their sector or just trends in the overall economy. So what we did was we downloaded the market returns for this same data set, only not as much of it was available, so we only using the last about 1,500 observations instead of 1,792. And we created a residual return series and then reran the experiment and found that nearly 2 times the number of asset pairings were marginally uncorrelated than they were before. So we had 36% marginally uncorrelated when the market was in, and 60% when the market is taken out. And then 14% are conditionally independent when the market is taken out, compared to 6%. So the market was accounting somehow for about, you could say, about half of the overall covariance between the different assets. So that's basically the talk. So this sort of thing has been done in finance before. A guy called Stambaugh wrote a paper in '96, but he showed how it could be done with 22 assets, and of course more than 22 responses. And I've shown how it can be done with a lot more than that. And I've argued that even when ordinary least squares suffices, the parsimonious approach has merits. You could think about how to estimate the stability or measure the stability, and the bootstrap is certainly an easy way to do that conceptually, but then the algorithm becomes very computationally intensive. All of these bootstrapped cross-validations and things like that would take quite a long time. But I do plan to implement it, and also to compare it to an alternative Bayesian approach that I've been working on for the last few months that is not quite ready for presentation. But the version of the R package does include the ability to sample from the posterior distribution of this monotone missing data posterior. And we'll see how that works out. And Ricardo and I have been working a little bit on how to relax the multivariate normal assumption by considering a class of models that uses copulus. But unfortunately, that's not what he's talking about today. So thank you very much for your attention.
One quick question, maybe?
I guess just a question about the model that you have in mind. So you're thinking of, suppose you get a complete observation, right? Then you have what? Multivariate stationary time series, or you have IID vectors?
Right. So we're the return series are not as long-term correlated as the price series would be. So we are making an assumption of independence, and the time aspect is not coming in, and we're just interested in how observations for a particular time are correlated with one another. But it would make sense to try to fit an AR model or something to these residuals, so to these returns, and then do this on the residuals or something like that, or do a big hierarchical model where the marginals are some kind of time series, and do some kind of vector autoregression or something like that, but we haven't done that.
Well, thanks again.
Thanks.